We actually did some chemical reactions in the lab last Wednesday. Wednesday's our lab day, right? One that we did was this guy. We took sodium hydrogen carbonate and HCl. Oh, actually, we didn't do it the fun way here. We did it in solution. This is just a little pile of the solid here. Added the HCl directly to it. They won't let you do that because there's a lot of stuff going up and it can blow acid out the top and stuff. So you had the boring version, just kind of, the solution with just a few bubbles in it. So it'll get there in a second. So yours just kind of looks more or less like this. Not nearly as exciting or fun. But we're going to do chemical reactions today. This is an example of the chemical reaction you did. Sodium hydrogen carbonate, HCl, giving CO2, water, and sodium chloride. Now, we've talked a little bit about chemical reactions in the past. We saw that bromine and aluminum could react. They would undergo a chemical change. Aluminum is a metal. Bromine is a liquid at room temperature, high vapor pressure. Therefore, there's always lots of bromine vapor above it. This is sealed up. When these two are mixed together, as we've seen, they form aluminum bromide. This is a white solid. It has totally different physical and chemical properties than the stuff we start with. This is a chemical change, isn't it? When we have a chemical change occurring in chemistry, we can write a chemical equation describing that chemical change. Typically, we will put reactants on one side, we will use an arrow, and then we put the products on the other. Now, the arrow in a chemical reaction like this, a chemical equation, is a special kind of arrow. It has the same properties as an equal sign in mathematics. And what that means is that there must be the same numbers and types of each atoms on both sides of the equation. We also will see there must be the same mass on both sides of the equation. As we look at this chemical equation describing aluminum and bromine, we see that there are two aluminums that react with 3 molecules of Br2. Remember, bromine is diatomic. And we're going to form 2 of the compound aluminum bromide. You'll also note in this equation we have little letters following the compounds and elements. Those are actually optional in a chemical equation. Sometimes you'll put them in if you want to be clear. Sometimes you can leave them out. They stand for solid, liquid. G is gas. AQ is aqueous. That means something is dissolved in water. We have solid aluminum, liquid bromine, going to aluminum bromide, solid. Now, in order to make sure that our equal sign, that is our reaction arrow, is respected properly, we must insert coefficients. So here's the 2, the 3, the 2. These guys must be inserted into our chemical equation so that we have the same numbers and types of atoms. Instead of simply talking about this in terms of atoms, we can also talk about this using the mole concept. We can read this equation simply as saying 2 moles of aluminum will react with 3 moles of bromine to give us 2 moles of aluminum bromide. Now again, just to make sure you get it, on this side of our equation, we have 2 aluminums, don't we? On this side, we have 2 aluminums. We have 6 bromine atoms on this side. And we have 2 times 3 is 6 bromine atoms on this side. This equation is what we refer to as balanced. That is, it has the same numbers and types of atoms on both sides. When we speak of a chemical reaction like this in terms of moles, we use the word stoichiometry to describe that. Now, as I've said before, stoichiometry is a wonderful word. It sounds so incredibly complex, but it really isn't. It simply describes a chemical reaction in terms of molar quantities. Any questions? Well, we could describe this equation using moles like this. Or, remember what we did last chapter in terms of mass ratios, not just mole ratios, but mass ratios. Whenever we speak of 2 moles of aluminum, there's a mass that corresponds to that. So we could also say that we have 53.96 grams of aluminum. Look at your periodic table, that's the molar mass of 2 moles of aluminum, reacting with 479.4 grams of bromine to give us 533 grams of aluminum bromide. So this is nothing more than the concept of molar masses applied to stoichiometry. This is how we will do chemical reactions very quantitatively. If I gave you this and I said that you had 53.96 grams of aluminum reacting, you could very easily say, okay, if that's the case, I should get 533 grams of product. Simple stoichiometry. Also note, if you add up 53.96 and 479, you get 533. This is the conservation of mass that we learned from Lavoisier back in chapter 3. The mass is the same on both sides. All right. These little coefficients that you have to insert in a chemical equation. This is the process of balancing an equation. Now, there are lots and lots of ways to balance equations. What we're going to do is kind of by inspection. So when you do it by inspection, you look at it, you wave your arms a little bit, you kind of fiddle here, fiddle there, and it winds up right. You can also do it with an algorithm. There's a fancy algorithm you can use for it. There are computer programs that do it. There are as many ways to balance equations as you want. But we're going to do it by inspection and typically using what I refer to as the even-odd method. Because I think that's the simplest and the easiest to understand. Now, we've all seen hydrogen peroxide before. Again, this is the fizzy stuff that you pour on cuts and whatever. It decomposes to form oxygen as a gas, that's the fizzy part, and liquid water. This is the equation for what's happening. But if you note, this equation is not balanced, is it? If you look at this side, we have 2 hydrogens and 2 oxygens. If we look at this side over here, we have 2 hydrogens and 3 oxygens. So this equation is not balanced. what we want to do is simply look at it, fiddle with it, and see what coefficients we have to put in order to make it balanced. Now in the even-odd method, what I do is I look to see if there's something odd on one side, even on the other. And the oxygen is a good example here. We have an even number of oxygens here and an odd number of oxygens here. The first thing that I do is I look and I say, is there something simple I can do to make it even on both sides? Well, if we put a coefficient here in front of our water, where we only have one oxygen, now we have 4 oxygens on both sides, on this side, 2 on this side, but they're both even. So we start off just by sticking in our coefficient 2 to make our oxygens both even on both sides. All right. By doing this, we wound up with 4 hydrogens on this side, didn't we? And we only have 2 hydrogens on this side. We also have 4 oxygens on this side and only 2 on this side. We can fix both of those problems simply by sticking a 2 in front of our hydrogen peroxide. Now, if you add it up, we have 4 hydrogens, 4 oxygens, 4 hydrogens, and 4 oxygens. We have just balanced this equation. Now, this is kind of like working a crossword puzzle sometimes. But with a little bit of practice, it's actually not difficult. The equations that we work with in 110 are going to be straightforward, pretty much like this one. And I think that everyone's going to have a great time doing this. I know I do. Let's look at another example. What if I put on an exam that I had solid potassium chlorate decomposing to form oxygen gas and potassium chloride? And suppose the problem was to write this equation and then balance it. Well, first of all, you have to figure out what potassium chlorate is. Remember, I told you you had to remember those things. What is chlorate? ClO3 minus 1. Potassium group 1 metal plus 1. So this is just KClO3. Now I say oxygen gas. Oxygen, you recall, is one of our diatomics, isn't it? So that's O2. And potassium chloride, group 7, group 1, that's just KCl. So we're starting with this. Solid potassium chlorate, oxygen gas, and potassium chloride. Now we have to balance the thing. As we look at this, we have 3 oxygens on this side. We have 2 oxygens on this side, right? That's an odd even. We could remedy that simply by putting a 2 in front of our potassium chlorate. There's a bit of symmetry here that also works that'll get you to the answer fairly quickly. Remember when we were making compounds and you had something like aluminum oxide? I said you could take the charges and just cross them down Oxygen was -2, aluminum was +3, so aluminum oxide would be aluminum 2, and 3 oxygens. It's crossed over. You can do the same thing in most chemical equations. We have a 2 and we have a 3. We said we're going to put a 2 here. We also are going to take this 3 and put it here. Now you can do this stepwise. You don't have to use the crisscross. If we stuck our 2 in to double this would now give us 6 oxygen, right? That's where the 3 comes from, 6 oxygen atoms. All right, what's missing here? We have stuck in 2 in front of our potassium chlorate. That gives us 2 potassiums, 2 chlorines. We need 2 KCl's. And we have balanced our equation. Now, while we're talking about potassium chlorate, I don't think we do it in lab. That's a shame. Can't do fun things anymore. But this used to be the standard way to make oxygen in the lab. You would take a little bit of solid potassium chlorate, and you would put it in a test tube, heat it over your Bunsen burner. It would kind of melt, start to bubble a bit. When it did, it evolved oxygen gas. How did you know it was oxygen gas? Well, you did a really neat thing. You took a little piece of wood, so something like a popsicle stick, and you stuck it in the flame of your Bunsen burner, so it lit on fire. Then you blew it out, but you still had red embers on there, right? And you took that, shoved it down your tube. When it hit the pure oxygen, it immediately burst into flames. Oh, it was so exciting. So much fun to do. But too much fun. Can't have that much fun in lab. But here's another thing that's fun that you also can't do in lab. Same sort of experiment. Again, we're going to take potassium chlorate, going to heat it to make oxygen and KCl. Instead of sticking a wooden stick down the tube, this is a gummy bear. Now, if you have small children, they might find this disturbing. Here comes our gummy bear. Here's our potassium chlorate. Ooh, ow, owie, owie, ooey. And there goes our gummy bear. As you see, it's just a really fun thing to do. And it's all gone. Now, what's happening here is that the gummy bear is essentially pure sugar. Okay? So the equation you have is sugar, so we'll use C6H12O6, plus potassium chlorate, give KCl. This stuff burns immediately with the oxygen to give CO2 and water. Why don't you just quickly balance this equation? Well, this is an odd even thing as well, isn't it? Because we have 1 carbon here, 6 carbons there. You could double this and then work your way up. Often, if you have something with lots of atoms in it, so something like this, it's easier just to start with this guy. So if we have 6 carbons here, we're going to get at least 6 CO2s, right? At least. We have 6 oxygens, so we will get at least 6, well, We need 6 oxygens here, so we have, let's see, 6 of them tied up here. That's 12. Gee. Oh, we have KClO3 too. Whatever. We have 12 hydrogens. Going to need at least 6 waters. So at least 6 here, at least 6 here. Then you would figure out how many KCl's you need to give the extra oxygen. Oh, it turns out something like this. 4 KClO3s, 6 CO2s, 6 waters, and 4 KCl's. By the end of this chapter, you should be able to balance this. You might not be happy doing it, but you'd find it very satisfying. Any questions? I can't tell you that no gummy bears were harmed in the making of this. All right. Here are some equations. Balance them. Now you see the advantage of having the mini prints is you don't have to write any of this. Talk about them one at a time here. Even number of hydrogens, odd number of hydrogens, right? So we're going to want to double this. So let's start off by putting a 2 here. That gives us 2 nitrogens, but that's okay because we have N2. So that works. So if we have 6 hydrogens here, how many H2s do we need? 3 of them. Do your next one. We do have an odd even here. 1 hydrogen, 2 hydrogens, right? So let's double the amount of HCl. Put in a 2. That gives us 2 hydrogens, 2 chlorines. But that's okay, we need 2 chlorines. 1 zinc, 1 zinc. Only thing you have to do is stick in this 2. What is this stuff called? Iron 3 oxide. And this is iron 3 chloride. Well, we have 3 oxygens here, we have 2 here. Right? So we're going to start off by doubling this guy. Okay? Now that's going to give us 4 irons. So we're going to need a 4 right here, correct? How many oxygens? We have 2 of them out here, 2, our coefficient's 2. That's 6 oxygens. So we're going to need a 3 right here, correct?
Yeah.
How many chlorines do we need to make this work?
6.
Well, we have 4 here, so 4 times 3 is 12. Comes in pairs, doesn't it? So we need 6 of them. Now you see, I told you that was fun. Let's do it again. We have 1 sodium, 2 hydrogens, 2 hydrogens, 1 oxygen, 1 O. I miscounted. 3 hydrogens, right? Only 2 on this side. So I would start off by putting a 2 here, doubling that. Now if we do that, we need 2 sodiums, don't we? So let's see. We have a 2 here, a 2 here. That gives us 1, 2, 3, 4 hydrogens, 2 oxygens. So we have to double this as well. 2, 2, 2, and 1. One hydrogen, 2 hydrogens. Put a 2 here, that doubles it, right? So we're good, we're even. That also gives us 2 chlorines, but that's what we have. 1 lead on both sides. Again, all you have to do is stick the 2 in here to make it work. Silver nitrate. Now silver is actually a transition metal, but silver is going to always be +1. So we don't need to call this silver 1 nitrate, just silver nitrate works. Okay, we have 1 silver on both sides. We have 2 nitrates here, don't we? And only 1 here. So we're going to have to double the number of nitrates we have by putting a coefficient out here. That means we have 2 silvers now, so we need 2 silvers here. Coefficient of 2. That gives us 2 chlorines, but that's what we've got. So, sticking in those 2 coefficients, we have a balanced equation. So isn't that neat? Now, of course, there is a tutorial dealing with balancing equations. Look at this equation and let's balance it. What you do on the actual tutorial, there are little fields here for entering numbers. The thing that you must do on the tutorial and on Blackboard is use the coefficient 1. In a real equation, if the coefficient is 1, you don't include it. But here you have to have a number or it will mark you wrong. All right, as I look at this, we have 2 carbons on this side. We have 1 carbon on this side. Odd even thing, right? So let's double our CO2s. Now we have 1, 2, 3, 4 hydrogens here. We have 2 hydrogens here. So we're going to have to double the amount of water. Now you look at it and you say, how many oxygens do I need to do this? Well, let's see. That's 4, 5, 6. I need 3 O2s. Anybody know what a bang sight cannon is? You can actually still buy them. I got one for my son. It's great fun. You take calcium carbide, add it to the tank, has some water in it. When the calcium carbide hits the water, it reacts and forms acetylene gas. Acetylene gas, of course, is explosive, isn't it? So it hits the water, it fizzes for a second, then you have a little spark device. You go like this, kind of like the striker you use, and it goes kaboom. Really neat. Yep, really neat. So let's balance this equation. We have 2 carbons here, we have 2 carbons here, that's good. We have 1 oxygen, we have 2 oxygens. We have 1, 2, 3, 4 hydrogens. We only have 2 hydrogens. We can solve a lot of these problems simply by sticking a 2 in there, and that's all we had to do. Any questions? All right. If you visit Blackboard, and I hope you do this all the time, you will find a link where you can download a balancing equation worksheet. This probably has 40 or 50 or so reactions on it. Now, at least 2 of these have big coefficients, and they're somewhat challenging. But most of them are entirely doable. There's also a thing called balancing equations answers, which you can also download. I suggest you do the problems first, and then the answers, and take a look at it. Practice these, because on Monday, we have lecture on Monday, right? We have lecture Monday. On Monday, at the end of chapter 5, we will have a quiz in class, and it will consist of 10 balancing equation problems. Okay? So practice. All right, types of chemical reactions. We are going to take chemical reactions and just divide them into groups. The reason for dividing them up at all is if you have an idea of what type of reaction you're dealing with, it helps you in guessing the types of products you're going to get, predicting products. Synthesis and decomposition reactions. These are actually very simple. You're starting off with 2 or more things, and you're winding up with something new. Decomposition is just backwards. You start off with something, and you break it into 2 or 3 more things. An example, if we take carbon and oxygen, we can react them and form carbon dioxide. We refer to this specifically as synthesis from elements. We'll also see later that this is called an oxidation reduction reaction. We've done a synthesis reaction in lab. Remember, we took copper, we heated it up, got that black goo on it, rubbed it off on a chem wipe. That was copper 2 oxide. That's a lot of it. You just had a little bit. That, again, is a synthesis reaction starting with elements. We can also do synthesis reactions with compounds. This is an example from organic chemistry. Here we're taking ethene, carbon-carbon double bond, reacting it with hydrogen bromide to form what's called bromoethane. Again, we have added two things together, taken two things, made something new. Synthesis reaction from either elements and compounds, or compounds themselves. Decomposition is simply synthesis backwards. We start off here with copper 1 sulfide. How do we know that's copper 1? Because sulfur is -2, isn't it? We have 2 coppers, they must be +1 each. Copper 1 sulfide, if you heat it up, will give copper and sulfur. Calcium carbonate. If you take calcium carbonate and you heat the heck out of it, you can decompose calcium carbonate to calcium oxide and CO2. So here we have a compound, and we're decomposing into compounds. This is actually a very important reaction, because what do you use calcium oxide for? That's the lime that goes into cement. Okay? So, calcium carbonate, something you dig out of the ground, that's limestone. You heat the heck out of it. You make calcium oxide. Mix it up with lots of little rocks and water, this gray stuff, and it sets hard. How does it do that? Calcium oxide reacts with CO2 in the air and makes calcium carbonate, which we just said is rock. See, there's chemistry everywhere. We did a decomposition in lab. We took ammonium hydrogen carbonate, we heated it up, and we had this horrible smell of ammonia, didn't we? Ammonia, CO2, and water. Is this equation balanced? One nitrogen, 5 hydrogens, 1, 2, 3, 4, 5. 1 carbon, 3 oxygens, 1, 2, 3. Yep, it's balanced. Replacement reactions. Replacement reactions come in 2 types. We'll call them single replacement and double replacement. In a replacement reaction, elements or elements and compounds will react to give new elements and compounds, or in a double replacement, we will take and simply exchange ions in ionic compounds. Examples. If we take, what is this stuff? Lead 4 chloride, and react it with fluorine, we get lead 4 fluoride and chlorine. We have a compound and an element making a compound and an element. We have replaced the chlorine in our compound with fluorine. Single replacement. Deja vu here. So this is what we just looked at, our single replacement reaction, right? We did one of these, didn't we? Remember our nail that we took and we put in copper nitrate. That was iron reacting with copper 2 nitrate to give iron 2 nitrate and deposit copper metal. Copper metal was a little red stuff right there at the end of your shiny iron nail. Single replacement reaction, compound and an element, compound and an element. The double replacement let me just say this. In a single replacement reaction, there's a rule of thumb. Metals will always replace metals. Non-metals will always replace non-metals. In our copper reaction, the copper was a metal, the iron was a metal. In this reaction, fluorine is a non-metal, chlorine's a non-metal, and they swap. Metals, metals, non-metals, non-metals. Now there are actually two very important exceptions to that, but we'll talk about them later. As I said, this is a double replacement reaction. Double replacement of ions. If you think about this, this is silver nitrate. In solution, this will form silver and nitrate ions. This will react with a solution of sodium chloride, sodium and chlorine ions. When they react, they simply swap ion pairs. Silver pairs up with chlorine, sodium with nitrate. It's a double replacement of ions. Some books call these displacement reactions, not replacement, but whatever. Any questions? Finally, perhaps the most interesting and maybe the most important of the group are oxidation reduction reactions. These are called redox reactions, redox. In a redox reaction, elements will change oxidation state. Now we talked about oxidation state. We've been saying it all day. Lead, 4 chloride. Remember, there are other rules relating to oxidation state. We'll review those. So we can talk about the oxidation number for all of the elements in a compound. For example, I said that our carbon plus oxygen to give CO2 was a synthesis reaction, but it was also a redox reaction. Now here, carbon and oxygen are elements. Remember what we said about oxidation numbers. They compare the element in the compound with the element on the periodic table. Well, here they're the same, so their oxidation numbers are 0. Oxygen. We said that oxygen was always going to be -2, isn't it? That was one of the rules, the only rule really that we remember. Halogens -1, oxygen -2. Well, that means we have 4 negatives here, which means that this carbon must be a +4. By definition, these guys are 0. Over here, our carbon is going to be +4 to balance the 2 negatives from our oxygen. Oxidation numbers of both elements have changed. And that makes this an oxidation reduction reaction. Now we'll get lots of practice at this. Don't worry yet. You'll worry later. All right, are these synthesis, decomposition, or replacement reactions? Well, here we're taking two things and we're making one. That's called synthesis. We're actually doing it from the elements. All you really need to say is synthesis. How about this guy? Compound in an element, compound in an element. It is a single replacement, non-metal replacing non-metal. And our last one, we have aqueous solutions of sodium sulfate, barium chloride. We're making barium sulfate and sodium chloride. This is a double replacement reaction. We have hydrogen peroxide. We are letting it form oxygen and water. I almost said the word decompose, didn't I? This is clearly a decomposition reaction. One thing forming two others. Phosphorus trichloride, a molecular compound, reacting with chlorine gives phosphorus pentachloride. Two things, we're making one. Synthesis. And finally, iron 3 oxide plus chlorine to give iron 3 chloride plus oxygen. Non-metal replaces non-metal. Single replacement reaction. Any questions just on the simple nomenclature here? All right, as we've done reactions in lab, some of you have said to me, how do we know that's what's forming? Well, I kind of said something like, you just got to figure that out. That's what you do in chemistry, right? Well, what we're going to do is talk about how you figure that out. Just basically how you predict what might be forming. The really fun thing in chemistry is trying to confirm later on exactly what happened. Now, we've seen this before, aluminum reacting with bromine. I'll just start the movie because it's a neat movie. Take a little bit of aluminum, dump it into a beaker of fuming bromine. We get lots and lots of heat evolved, lots of very, very toxic bromine gas going everywhere. Don't do this at home. And when you're done, we're left with a little crusty patch of a solid around the outside. Now, how do we predict? This is obviously going to be a synthesis reaction. In order to predict this, what you want to do is look at your reactants. Aluminum's a metal. It makes sense that we're going to form an ionic compound because metals give ionic compounds, don't they? Aluminum will typically form a +3 ion, won't it? It's group 3. We know that bromine, group 7, halogen, is going to form a -1 ion. And so if you had to give your best guess as to what would happen here, you would say we're going to pair the aluminum with the bromine and make AlBr3. Now once again, this equation is not balanced, is it? So quickly balance it. We have even bromines, we have odd bromines. I would start off by putting a 2 here. Now, that gives us 2 aluminums here. So we need a 2 out here. And we have 6 bromine atoms. We need 3 moles of Br2. Any questions? All right, let's say we had hydrogen reacting with oxygen. Now again, we've seen this, but it's kind of a really neat movie too. There's our very brave chemist, a balloon filled with hydrogen, a balloon filled with oxygen, and whatever. Now you look at these, both of these are nonmetals, aren't they? So we're not going to make an ionic compound. We're going to make a molecular compound. So instead of looking at charges here, what we do is we look at these elements and we decide how many bonds they're typically going to make. Oxygen is group 6. It has 6 valence electrons. It needs 2 electrons. Typically, this will be 2 covalent bonds. Hydrogen, group 1, has 1 valence electron. It will form 1 covalent bond. So once again, our best guess as to what's happening here is we're simply making water. Again, we're not balanced. One oxygen, 2 oxygens. We need a 2 right here. That's 4 hydrogens. We only have 2. Need a 2 out there. So 2 types of synthesis reactions. One where you make ionic compounds, one where you make molecular compounds. Look at, for an ionic compound, look at typical charges and construct a best guess. For molecular compounds, look at typical valence. How many valence electrons, how many bonds do you have? And again, give it your best guess. Now, decomposition are actually much more difficult than that, because lots and lots of strange things can happen during decomposition. This stuff is nitrogen triiodide. It's a solid. This is a ring stand. And this is filter paper. Now when you make nitrogen triiodide, what you do is take ammonia and you add iodine. That's all you have to do. It reacts very quickly and forms this very dark stuff, little powder, of nitrogen triiodide. You very carefully take your tube with this stuff in it and you filter it through a piece of filter paper. So what this is filter paper just with a little black spot in the middle. where we filtered off the ammonia or nitrogen triiodide. Then you let it dry. And you do all of these things very, very, very carefully. Why? Well, this is a feather. And in super slow motion, this is one of the most sensitive contact explosives that there is. Literally, touch it with a feather and it goes boom. All right. Now, when something goes boom, lots of stuff can happen. That's why decomposition is so difficult. But what you do is you kind of look at, what's left over. See the big purple cloud? That's iodine. We all know iodine is purple. So my best guess is we're going to be making iodine here. If we're making iodine, our nitrogen is probably going to wind up simply as nitrogen itself. Now, many explosives, most explosives, are really based on the fact that nitrogen N2 is a very, very stable compound. And nitrogen bonded to other things is much less stable. So nitrogen has a great tendency to go downhill energetically to make N2. When it does, makes lots of gas, big explosion. That's how TNT, plastic explosives, all that stuff, that's how it works. So, let's balance this equation. Well, we have an odd number of iodines, an even number of iodines. Let's double it out here. That gives us 6. If we have 6 iodines here, we need 3 here. We just put in 2 nitrogens. We have to. I think that that's balanced. No, they will not let us make that in lab either. All right, we said single replacement, there's a rule of thumb. Rule of thumb in single replacement is that metals will replace metals, nonmetals will replace nonmetals. So if I tell you we have lead 4 chloride reacting with fluorine, quickly write the products. Well, lead is going to be +4 here, so that means it's +4 in our product. We're going to swap the 2 nonmetals. So we're going to get lead 4 fluoride. Chlorine will form the molecular chlorine Cl2. Are we balanced? No. So balance it. We don't have an odd-even problem here, do we? But We do have 4 fluorines here and only 2 on this side, so let's double that. We have 4 chlorines here, only 2 on this side, so let's double that. I think our lead works out okay. Now, you know, I said that there were 2 exceptions to our metal-metal, non-metal rule. And unfortunately, you do have to kind of remember these exceptions because these are probably the most important examples of double replacement, single replacement reactions. This is a single replacement where we're using hydrogen gas or carbon. If we take copper 1 oxide and we react that with hydrogen gas, if we did our non-metal rule, we would expect hydrogen and oxygen to simply change places. Well, we don't. Hydrogen and carbon both in these types of reactions will act as if they are metals. So just remember the 2 exceptions, they're acting as if they are metals. So, hydrogen is replacing copper to make water. This is our compound, an element, our new compound, new element. Carbon, the same sort of thing. Carbon's a non-metal. It does not replace the oxygen, however. It pretends it's a metal, replaces the iron, so we get iron metal and CO2. Why are these important reactions? Well, this is what they do all day in Gary, isn't it? Take iron 3 oxide, iron ore, and carbon, that's coke, heat it up together in these giant smelting furnaces and pour off molten iron. Same thing with refining using hydrogen gas. We've made copper. 2 very important reactions, the things to remember. Hydrogen and carbon act as if they are metals. All right, double replacement reactions are kind of the simplest once you get used to the concept. The cation will replace the cation, anions will replace anions. So if we have potassium sulfate reacting with barium nitrate, we will simply swap components, and what will we get? Well, the potassium is going to pair with the nitrate, isn't it? And the barium is going to pair with the sulfate. Now, what I want you to notice here is that we've started off with 2 aqueous solutions, right? We wound up with potassium nitrate in aqueous solution. But what's this little s here? That's a solid. We have made solid barium sulfate. In order for a double replacement reaction to go, you must form a solid or a gas. These are also called precipitation reactions. Double replacement here. We take potassium iodide in solution, lead nitrate in solution, lead 2 nitrate. We will wind up with solid lead 2 iodide and potassium nitrate left in solution. You see, we start off with 2 clear solutions. As soon as they mix, we form lead 2 iodide. Lead 2 iodide is a solid. It's insoluble in water. If we sat and watched it, it would fall down to the bottom and give a little yellow plug. This is said to precipitate. Double replacements are also called precipitation reactions. If you do not get a precipitate or a gas, nothing happens. It's not a reaction at all. All right, so everybody's sitting here saying to themselves, that's good, okay, fine. How do I know that lead iodide is insoluble? How do I know that? Well, because you looked at the solubility rules. Rule number 1, if you have a group 1 metal or ammonium, it's going to be soluble. Forget about it, it's soluble. Okay, group 1 and ammonium, soluble. If you have a nitrate or an acetate as your anion, it will be soluble, period. If you have a metal halide, it will be soluble unless the metal is one of these 4 heavy metals, referred to as heavy metals, way back before there was music. Silver, lead, mercury, and copper 1. All of those halide salts are insoluble. If you have a sulfate, it's going to be soluble, unless you have barium, calcium, or lead 2. If it's a metal hydroxide, and it's not governed by Rule 1 here, it will be insoluble. And finally, same thing for carbonates, unless it's governed by Rule 1, they will be insoluble. So hydroxides and carbonates, insoluble unless the Rule 1. These guys are always soluble. These guys are going to be soluble except for the heavy metals and these 3 guys. Do you have to know these? Of course you do. Now I see some people are still writing frantically. I will pace and pause for a moment while you finish writing frantically, because we are now going to do a set of problems. Look at these guys and decide if they are going to be soluble or insoluble in water. Silver nitrate. We know that silver is one of those things that gives us trouble, right? But Rule 1 or Rule 2 said all nitrates and acetates are going to be soluble. Therefore, silver nitrate is a soluble salt. Magnesium chloride. All right, we remember Rule 3, I think it is, that halides are going to be soluble, aren't they? Unless they're one of our heavy metal guys. Magnesium is not one of the heavy metals. It is soluble. The ones that are not are silver, lead, mercury, and copper. Sodium sulfate. Virtually all sulfates are soluble, aren't they? Sodium is a group 1 element. All of its salts are going to be soluble too. This is a winner. Twice over. For the sulfates, the ones that are not are barium, lead, and calcium. Silver chloride. Most chlorides are going to be soluble, aren't they? Except for the heavy metal guys. Is silver heavy? Absolutely. Silver chloride, I'll just give you a hint, is one of the classic insoluble salts that you need to remember. Barium nitrate. We remember seeing barium somewhere. Barium forms an insoluble salt with sulfate, doesn't it? But virtually all nitrates are going to be soluble. Virtually all halides are soluble, except for the heavy metal guys. That is silver, lead, mercury, and copper. This is a nitrate. Virtually all nitrates are going to be soluble. Most sulfates are soluble except for barium, calcium, and lead. Hey, iron is pretty heavy, but it's not our heavy metal, is it? Halides that are not soluble are going to be silver, lead, mercury, copper. Iron is perfectly fine. And finally, what is this stuff? CH3COO minus. That's acetate, remember? That's what acetate is. virtually all acetates, even lead acetate, is soluble. Any questions? All right, well, there's one thing that I would like to do, if I can get this to work, before we go, and that's to elaborate just a little about what I said about if you don't get a precipitate, nothing happens. This is a cute little thing that I wrote a few years ago. What this is supposed to be is a beaker filled with water, and we have a bunch of salts here. And what we're going to do is put our salt in the water, and we're going to see what happens. Let's just start off with something simple, potassium nitrate. Goes in the water. It's going to ionize to the two ions, potassium ion and nitrate. And these are just going to sit there and bounce around merrily in solution. If I take and I add something like, barium nitrate to it, I have barium, potassium, and now 3 nitrates, and they're just all bouncing around, but there hasn't been any chemistry here, has there? If we evaporated this down, we would still get barium nitrate and potassium nitrate. Nothing has happened. Let's see. Potassium sulfate, we said, was soluble, right? It forms 2 potassiums, 1 sulfate. No problem. Is calcium sulfate soluble? Most sulfates are soluble, except for barium, calcium, and lead. Not soluble. All right, what if I took barium nitrate, put it in solution? Again, I get 1 barium and 2 nitrates just bouncing around merrily. And what if I took potassium sulfate in solution? 2 potassiums, 1 sulfate, all bouncing around. But what if I put them in together? Insoluble barium sulfate falls out, and I'm left with 2 moles of potassium nitrate. That's why no chemistry happens unless you get a precipitate or a gas. Any questions?